In this sample, we'll figure out the speed of a satellite that's orbiting at a certain altitude. This problem talks about the International Space Station, which orbits Earth at an altitude of 360 kilometers above the surface. The acceleration required to keep it in orbit while along a circular path is provided by Earth's gravity, directed towards the center of the Earth and hence towards the center of the orbit. Earth's gravitational pull decreases gradually with altitude. We'll talk about that later in topic 3. So acceleration due to gravity that's exerted on the International Space Station is only 8.78 meters per second squared. It might surprise you that that's not lower, but we'll talk about that later. We're also told that we're orbiting at an altitude of 360 kilometers. We're not going to plug that in anywhere directly, but we will use it. So we're going to find two things. We're going to find the orbital speed of the ISS, and we're going to find the time that it takes to complete one rotation. And I'm going to introduce a vocabulary word for you here. It's capital T, which stands for period. And for anything that's orbiting or going around in a circle, the period, or capital T, is the time that it takes for one complete time around the circle. So whether that is a test tube in a centrifuge or a star around a black hole in the center of a galaxy, period is the same thing. So those are the two things we're going to consider today. And the math is going to get a little messy, but if you listen and stop the video, should not be too much trouble. So in order to find the velocity, okay, hopefully you're thinking, well, we're given an acceleration, we need to find a velocity, and we're given a radius, more or less. That's the tact we're going to take. So we're going to go for this formula, v squared over r, and that is centripetal acceleration. I know I don't always put there. So we're looking for the velocity. We're given the acceleration. We need to find the radius. Now, when we have a satellite orbiting the planet, the radius we use is not the distance between the surface and the satellite. It's the distance between the center of the planet and the satellite, because that's what the satellite is really orbiting. So to get the proper radius, we need radius of the Earth plus the altitude. Okay, and so in a very bad drawing here, if this is the Earth and this is the ISS, the distance is really this, okay, and obviously this is not to scale. Here's the radius of the Earth, here's the altitude. We need to add those numbers together. So the radius of the Earth, which you could get from various sources, including somewhere in your book, is 6,738 meters, plus the altitude, which they tell us is 360 kilometers, so that's 360,000 meters, okay, for a total of 7,098,000 meters, or 7.098 times 10 to the 6 meters. Okay, so that's the orbital radius of our satellite. So let's see. Centripetal acceleration is v squared over r. V squared gives us centripetal acceleration times r. I hate to write the square root sign. I really do. So I usually just stick with v squared, okay? Our centripetal acceleration is 8.78 meters per second squared. Our altitude is, maybe not round that to 7.098 times 10 to the 6 meters, right? You can see from the units, I'm going to get meters second per meter squared per second squared, which is what I want. Because when I take the square root, then I'm going to get 7,900 meters per second for my orbital speed for this satellite, 7,900 meters per second. Now, if you look in the book and solve and look through this solution in the book, they tell you they're going to add Earth's radius to the 360 kilometers, and then they don't do it. So their speed is slightly slower than my speed here. So be careful, especially if you're going to use the book a lot. Put a sticky note in your book, something like that. They literally tell you to do it, and then they don't do it. So they get like I said, a speed that's slightly slower for velocity. Then we need the time for one orbit, okay? And like I said, that's called the T for the period. All right. And so when we do this, since we have these objects that are uniform circular motion, means the speed is constant. The velocity is changing, but the speed is constant. And the great thing about that is that we can just use distance equals speed times time for this. Okay. So to find the period, we need the distance for one orbit divided by the velocity. And so to find the total distance traveled by this satellite in one orbit, we need 2 pi r, okay? 2 pi r, 2 pi times our radius, 7.098 million meters, divided by our orbital velocity, which we just found was 7,900 meters per second. And you get 56.45 seconds, which I usually convert into a more reasonable unit, so 94 minutes. Okay, so 94 minutes for once around. And if you've ever gone out while the space station is actually visible, that is exactly how long it takes for it to go around. It's pretty easy to locate when it's going past. It's moving by far faster than anything else in the sky, and I've been out and timed that is just about an hour and a half. So little pitfalls here. Probably the biggest pitfall is adding the orbital radius to the radius of the Earth. And then sometimes we get mixed up in the units there. So just be clear with yourself and make sure you realize what's orbiting what. And this should not be too much trouble for you.